Hi, everybody. Thanks for coming to this presentation. My name is Joe Durkin, and today I'm going to talk about a new approach that will enable us to make use of elastic deformation observations at GNSS stations in Antarctica to ultimately put constraints on specific regions of mass loss on the continent. So this map shows the average rate of ice loss in Antarctica during the last decade. Each year, it lost about 120 billion tons of ice, and this drives the elastic deformation response of the continent with rates of up to about 2 centimeters per year in the vertical and about half a centimeter per year in the horizontal. So the question that we want to ask is, given the current distribution of GNSS sites, can we use these GNSS observations of elastic deformation to put constraints on how the ice is changing at specific regions of interest, like what has been done in Greenland and many other parts around the world? We developed a new technique that makes use of the relative deformation among collections of GNSS sites to demonstrate that the current configuration of GNSS in Antarctica can resolve mass change at individual glaciers. To get there, one of the questions that we need to know the answer to along the way is, what is the ice loss that each GNSS site is responding to? We can answer this by taking the way we typically model elastic deformation and flipping it on its head. On the left is a cartoon showing how elastic deformation is usually modeled. So a disk is placed at the origin, and the deformation that it induces is expressed as a function of the distance and the angle from that disk. So what we do instead is to put the observer at the origin and keep track of the deformation that's observed there due to loading from a disk that's placed some distance and some angle away. And what we call this is a load sensitivity kernel. This is an idea that builds on techniques that were used by Surendra Adhikari in a 2017 paper, and also by Duncan Agnew in a 2000 paper. To demonstrate the load sensitivity kernel, I've centered it on the INMN GNSS site in the Amundsen Sea region. The Amundsen Sea region is important because it hosts glaciers that lose a prodigious amount of mass annually, namely Pine Island Glacier, Thwaites Glacier, and the Kohler glaciers, with their regions of significant dynamic thinning outlined in black. So if we take this load sensitivity kernel and center it on one of the GNSS sites, for example, INMN in these figures, what we get is a map in which each pixel represents the contribution that a disk with a height of 1 meter filled with water would induce at a GNSS site. And this is shown for the vertical and the horizontal components. And if we take this load sensitivity kernel map and multiply it by our map of ice mass change, what we get is a map that shows us how much each disk of ice loss contributes to the elastic deformation signal observed at INMN. So INMN in total has an elastic uplift rate of about 10 millimeters per year. This is the result of the sum of many, many, many disks, each of which contribute between a few microns to a few tens of microns of elastic deformation per year. Disks that are closest to INMN with fastest thinning rates contribute the most to the site's elastic uplift rate per disk. But for example, regions near the grounding line of Pine Island Glacier. But there's not very many of these disks, and if you move further away from INMN, although the contributions of each disk becomes very small, the number of disks increases quite rapidly. So a common assumption that gets made is that because INMN is close to Pine Island Glacier, it derives almost all of its elastic deformation from the losses of Pine Island Glacier. However, this map demonstrates this isn't the case. If we look at Thwaites and PSK glaciers, each of these contribute about as much to INMN as the upper regions of Pine Island's dynamically thinning branches. And in fact, Thwaites and PSK contribute or constitute about 20% of INMN's elastic uplift. And what we found here is that far field mass loss is very important in correctly describing this site's elastic deformation. In fact, if you want to correctly account for 90% of INMN's elastic deformation rates, you need to consider all of the ice mass change within about a 300 kilometer radius And this is the case for both the vertical and the horizontal components. When we repeat this experiment at other GNSS sites in Antarctica, we find something that's very similar. This map shows the distance that you would need to consider to correctly express 90% of the elastic deformation rate for each of the GNSS sites. The overwhelming majority of these sites require you to consider ice loss within a radius of 200 kilometers or more to correctly account for their elastic deformation rates. And this is true, again, in both the vertical and the horizontal components. Far-field ice loss is a pervasive signal in the overwhelming majority of Antarctic GNSS sites. This means that if you wanted to use individual GNSS sites to put constraints on any particular glacier, it would be very, very difficult to do this because it would just not be very well constrained because each site is sensitive to ice loss over such a large area. So now the next steps that we need is a way to isolate deformation that originates from ice loss that we care about. One approach that has been used to isolate near-field ice mass loss is to look at differential displacement between neighboring pairs of GNSS. Now, that's illustrated here by showing the difference between INMN in blue and Backer in red. In these maps, all of the blue pixels show ice loss that contributes to the difference between these two sites becoming greater, and the red pixels result from mass change that causes this difference to become more negative. As you can see in these maps, looking at a differential pair of GPS does focus the areas of relevant ice loss, but it doesn't exactly remove far-field sources of ice mass change. We're able to isolate the deformation due to mass loss of a particular zone of interest using a new technique that utilizes all of the available GNSS sites and adding them up in a weighted series. So when you look at a pair of differential GNSS, differential GNSS deformation, you are looking at a weighted series, but a very specific weighted series. So in the case of the difference between a pair of GNSS, the first one has a weight of 1, and the second GNSS has a weight of -1. The rest have weights of 0. You can imagine that there could be different weights for each of the GNSS, and you could add and subtract these in the right way such that you minimize the contributions from outside some zone of interest. So, for example, to isolate the elastic response only from Pine Island Glacier, what we did was to solve for the combination of coefficients that minimizes the elastic deformation contributed by ice mass loss outside of this bounding box. And once we have these parameters, you can take the elastic deformation observed at the GNSS sites and add them up in the right way that it tells you how much elastic deformation Pine Island Glacier is inducing. And after we did that, it's shown in these maps. If the sum of these weighted series were to increase or decrease, that would be related to how much Pine Island Glacier's mass loss has increased or decreased, and not much else. It's possible to make these all three components of deformation here. Similarly, we're able to perform this at the Kohler glaciers, demonstrated here. And we can also do this at Thwaites Glacier, although in the case of Thwaites Glacier, we're only able to do this in the eastern component of deformation. And we can't isolate the elastic deformation due to the absolute mass changes of Thwaites Glacier. But what we can do is express mass changes near the grounding line of Thwaites Glacier relative to mass changes that happen at the Kohler glaciers. So to conclude this, what we found is that far-field ice loss is a pervasive signal in Antarctic GNSS elastic deformation. And this means it will be very difficult to use individual GNSS sites to put constraints on how specific regions are changing in their mass. This is just because the elastic deformation that a GNSS site is sensitive to derives from ice mass change over such an enormous area. However, we were able to use a new technique that considers the relative changes between collections of GNSS sites added up in a weighted series that isolates specific arbitrarily defined zones of interest, demonstrating that it's possible to use Antarctic GNSS to put constraints on mass changes of specific Antarctic glaciers with using the current configuration of GNSS sites on the continent. This has been demonstrated at 3 major centers of Antarctic ice mass loss, and it's applicable to many other regions on the continent, as well as other places around the world. So thank you very much for taking the time to listen to this talk. And if you'd like to contact me for discussing this in greater detail, please don't hesitate to reach out. Thank you.